Here's one last video to give you some tips about how you might approach design in Build Your Own World, and this I'm going to draw on a philosophy of software design chapters 4 and 5. Now some of this I've already kind of taught you, I've used some of these terms before, so it'll be repetitive, but I think it's worth repeating. So recall that one of the most important things that we can do when building programs is to hide complexity. The thing is, we, as I've said many times, are not smart enough to understand all the complexity of our programs all at once, and so we want to make sure that we're hiding that complexity from other programmers, from ourselves, from users. So using helper methods like getNeighbor to the west, or a helper class like input_device that abstracts away whether it's a keyboard or a string that's providing me with input, that hides complexity. So in the practice of modular design, which is closely related to this notion of hiding complexity, well, in an ideal world, John Oosterhout, in his books, basically says, wouldn't it be great if we could just break everything into totally independent modules? That would be the best possible case, because then the complexity of the system would basically just be equal to whichever module was most complex. However, that's not possible. So in the real world, modules need to somehow be able to talk to each other. So for example, you need to know the methods of other signatures in order to be able to call them. Now, quick note, when I say module here, it is not a specific technical term. So there is something in Java known as a module, but it's not that. Here when I say module, I mean it's an informal notion. It's either a class or a package or some unit of code that all does something specific. Okay, so it's kind of a vague notion, but I think it's an important one. Now again, as I said, it's not possible for these modules to be totally independent because they need to be able to talk to each other. So at the very least, you need to know the signature of the methods that you could potentially call. So in modular design, the goal then is we can't achieve the dream of total independence, so let's minimize the dependencies between modules, and in that way, we'll hopefully get a simpler system. Now he brings up the distinction between interface and implementation in this chapter, so I'm going to bring it up again. As you guys know, that's a really important distinction we've made. So for example, map is an interface, hash map and tree map are implementations. Disjoint sets, that's an interface or an abstract data type in this case. And there's many different implementations we might make of that same interface. Oosterhout has a nice quote in his book, which is that the best modules are those whose interfaces are simpler than their implementation. So why is that, and what does he mean exactly? Well, a simple interface would be, for example, something where you have like, say, an iterator which only has a hasNext and a next method, or even simpler, maybe just a getNext method. By having a really simple interface, well, that only gives you so many things you can do with a module. So someone using this class that only has a getNext method doesn't need to worry about like rewinding or something like that. The only thing you can do is call getNext, so that means using that module is very simple. Another reason is that if a module's interface is simple, and this is a little more subtle, we can change an implementation of that module without affecting the interface. So I'll give you kind of a silly example that drives this home. Let's say that the Java designers had included an array size method for the list interface, assuming that only array-based lists would be created. Well, that would mean that if you decided to build a linked list-based list, well, then it would be strange. You would need to change the interface in some way, maybe rename this method, something like that, and it would box you into a corner. But by keeping our module's interface really simple, we can change the internals without affecting the interface because the interface is so general and so abstract. The user doesn't need to know about the internals of what's going on. So in terms of an interface, I think it's important to note that a Java interface has both a formal and an informal part. The formal part is the list of method signatures. That's stuff the compiler checks. But there's also an informal set of a set of informal aspects to the interface, and these are rules for using the interface that the compiler has nothing to do with. So for example, if you build an iterator that requires hasNext to be called before next in order to work properly, which sometimes happens, then that's an informal part of the interface and generally considered bad style, but you could do it, you could tell the world, and that would become part of the interface. It's like rules of thumb. Another, if your add method throws an exception if you give it a null, that's an informal part of the interface. That's something that happens and you have to tell people about it in the documentation for your class or your module. Another example is the runtime for specific methods. So for example, the add method in the ArrayList class is expected to be constant time. If you change something about the class so that add is no longer constant time, that would be a change to the interface. People would get an observable change in behavior. Now, in terms of the informal parts of the interface, you can only really specify this in comments. I guess you could specify it in external documentation, but you have to write it out in English, and hopefully people look at it. And that's one of the reasons we want to ideally keep the informal rules for interfaces really simple, because we don't ideally want people to have to read a bunch of documentation to be able to use our modules. So I'll note here that you should be aware of the informal rules that you create for your modules as you work on Project 3. You can write them out, ideally, so that if there's something funny, just write it out so that you remember and it's something you can reason about explicitly. Another really nice notion in Oosterhout's chapter 4 and 5 of the book is that modules should be deep. So another quote I really like is that the best modules are those that provide powerful functionality yet have simple interfaces. I use the term deep to describe such modules. So as an example, the KD tree we did in our class is a deep module. In fact, most of the things we've created are deep modules. It has a really simple interface. There's a constructor that takes a list of points, there's a nearest method that takes a point and returns the closest point in the set, represented by the KD tree, and there's nothing informal that the user needs to know. Okay, there's no special rules for that the points need to be sorted or whatever else. Now it has powerful functionality. I can, underneath the hood, whenever it gets this list, it converts it into this complex searchable binary tree, and you spent some time putting that together. It arranges it in this KD tree shape. And the other thing is that the nearest method, it's actually fairly complicated as well. It has complex and very subtle pruning rules that are needed to be efficient, but from an external user point of view, they don't see all of that complexity. They only have a very simple interface, and it does something useful. Now, as you are trying to build modules and trying to make them deep in Project 3, I will say that one of the driving principles is that you want to practice information hiding. Okay? So one way to make your module deep is to hide as much stuff as you can inside the module. And what that means is you're embedding knowledge and design decisions that you've made in the module itself without exposing them to the outside world. Okay? That is, we saw some, I guess I'll come back to this in a bit, but we saw it in the earlier examples where we created an input device class, where you're hiding things inside of the module itself. You don't expose exactly how things are working. And this reduces complexity in a couple of ways. As we said earlier, it simplifies the interface, and it makes it easier to modify the system, as long as we're hiding things. Now, the opposite of information hiding is information leakage. And this happens all over the place with novice programmers, and particularly in this project. So this occurs when the same design decision is reflected in multiple modules, so that any change to one of them requires a change to all of them. So looking at this code from before, we have these two different move methods that process input in almost the same way. There's the code is very redundant. And so in this sense, we say that information or decisions about the design, they are embodied in two places. It is leaked across the boundary between these two pieces of code. You can think of these methods, I suppose, as a module, and that is causing, ultimately, this programmer a lot of grief. It makes it just much harder to reason about, makes it hard to fix anything. So Oosterhout points out rightly that information leakage is one of the most important red flags in software design, and one of the best skills you can learn as a software designer is a high level of sensitivity to information leakage. So you should be looking out like a hawk for things like this. Now, one last tip I want to give before we close out our discussion of software engineering for the day is that one of the biggest causes of information leakage is something known as temporal decomposition. The thing that leads students astray in this project is building a system, structuring a system that reflects the order in which events occur as the principal driving factor in the design. So let me be very specific. This is a very common bad pattern in Build Your Own World. Okay? So many students do something like this. If the game is started with an input string, you call interact with input string. In fact, we give that to you. This first bullet point is given to you. Now then the student goes through and parses the string given and finds the seed by finding the part that matches this pattern and gets the seed out of it. They then generate the world, and then maybe drawing on the example we've been working with in this lecture, they process each character using move, in the world each character that I've gotten out of the string. Now the other thing that can happen is calling interact with keyboard. So in this case, we need to display a menu and collect the seed. Then we generate the world, and until we're done, we're going to call move with keyboard world, some totally different method. Okay. Now, students do realize that maybe this world generation code should be reused, but there's a lot of information leakage across all these other aspects of the design. So for example, I often see students where the code that collects the seed, that parses the string and collects the seed, is completely disjoint from the version whenever you're interacting with the keyboard. Ideally, there should be one piece of code that collects single characters from some input device and it produces a seed. And it doesn't matter if that happened during interact with input string or interact with keyboard. The exact same piece of code collects and extracts the seed always. It should be shared between these two. But what temporal decomposition does to you is you start thinking of them as two totally different worlds, but really they have quite a lot in common. So some suggestions as you're embarking on Build Your Own World. I think it's very important to avoid unnecessary dependencies and get rid of obscurities by building classes that provide functionality that is needed in many places in your code. So if you need a random seed in two different places, make one method or one class that deals with that. Okay. Another is you should try to build what Oosterhout calls deep modules. They're, say, for example, classes that have simple interfaces that do complicated things. So if you're doing a room building algorithm or something like that, a world generation algorithm, you don't want to expose too many little nitpicky details to the layer above. You want simple interfaces that do complicated stuff under the hood, like KD trees, hash maps, and so forth. You should avoid an over-reliance on temporal decomposition, where the way you break down your problem is too closely coupled to the order in which things occur. Now, you will need to do some degree of temporal decomposition. It's only natural. But if you see that there's information leaking across the boundaries between different modules, then try and fix it. You should try to be strategic and not tactical. So an important part of doing this is not waiting too long to get started. Break up the work over time rather than putting it all at the end. And most importantly, above all, you should hide information from yourself when it's not needed. It will be so much easier to understand your code and to debug it and to interact with TAs at office hours if you've created really nice layers of abstraction where you're hiding information. Because at that point, you can now explain it to each other, you and your partner, you can explain it to TAs, you can understand it yourself. Okay, that's it for specific Build Your Own World programming tips. I know these tips seem kind of high level, maybe hard to digest, but I'm hoping that Project 3 will bring some of these lessons to life and you'll really see complexity staring you in the face and see how these tools can help you manage it.